Hello, my name is Hannah Fowler, and I am the project manager for ducting engineering, as well as the project lead for all the geotechnical components of our capstone design. We are happy to have you all with us today virtually as we give this presentation over our design, and we hope you enjoy. We are going to start off today with Dylan Loftus and the structural components.
Hi, my name is Dylan Loftus, and first we'll be talking about the structural component. Our project statement: the goal is to design the columns and beams for the office suite of the new engineering building at Tarleton State University. So at this point, all we're doing is simply selecting a layout for the columns and beams. Later on, we'll design them and figure out the sizing. Some of the criteria and constraints that we have to follow: the IBC, International Building Code, ASCE 7, ACI 318, and AISC, and as well as TMS 402. These are all different codes giving us constraints and minimum requirements. We have two different design alternatives, one being beams every 8 to 9 feet, while the other is beams every 6 feet. So our first one here will be beams every 8 to 9 feet. On the left here is an architectural drawing that was given to us in our problem statement. On the right is an AutoCAD drawing I've come up with to kind of help better visualize this. So these green marks here are all of our columns. Our red bars are our primary beams, while our white bars are our secondary beams. This is alternative 2. This is beams roughly every 6 feet. So same thing with the columns and the primary beams here. Columns in green, primary in red, and blue now is our secondary beams. As you can see, there are quite a bit more beams in here. On the left here, this is a drawing through the AutoCAD robot. You can see all of our, same here, all of our columns and all of our beams. And then here's two more figures of the drawing through the software, showing from first, second, third floor, as well as the roof line. Next will be Hannah Fowler talking about the geotechnical component.
Thank you, Dylan. As I said before, I am the project lead for the geotechnical components of our project. The goal of the geotechnical portion is to design the foundation for the office suite of the new engineering building at Tarleton State University. To ensure that the foundation meets the design standards, these 3 manuals will be used. Some of the constraints of the foundation is the structural load and the bearing capacity of the soil. This set of criteria determine the type of foundation that can be used. The 2 design alternatives that I found to be the most interesting, as well as sustainable, are using recycled concrete aggregate or energy piles. Recycled concrete aggregate reuses old crushed up concrete. It can be used in any foundation and has a better protection from seepage. It's often cheaper than other materials and preserves natural resources. Though it has a lot of pros, it may not be as strong if too much of it is used, and recycled concrete aggregate can be brittle, so thorough testing on the material would have to be done. The other alternative is energy piles. The pile shape is the same as if you were to design it normally, but you run a pipe through it for water to go through. At some depth, the temperature in the ground remains the same all year around. Water from a heating and cooling system goes through the pipe, and as it circulates will reach this average temperature, which is ideally going to keep the building at the same temperature all year round. Energy piles are environmentally friendly and have proven to save money on heating and cooling costs, and also typically use less electricity. They also have little maintenance cost. That's all I have on the design alternatives for the foundation design, and I will now pass it over to Jonathan Mink for the transportation component. Thank you.
Hi, my name is Jonathan Mink, and I will be doing the transportation component portion of the project. The design will be for a parking lot serving the office suite of the new engineering building at Tarleton State University. The criteria and constraints that will be followed will be using the ACI 330R01 guidelines for designs and construction that will be used to be calculating the pavement cross-section, layout of joints, and the joint details. The joint design will be sawing transverse joints to avoid cracking, and for steel reinforcement, we'll be using dowels and tie bars. Required material will be mentioned in the given alternatives and the design drawing and guidelines. Cost estimation will also be given in detail for each of the alternatives. For determining values and classifications using the ACI 330R01. Using that classification from Table 2.1, we determine the subgrade of soil to be sand and sand-gravel mixture with a moderate amount of silt and clay. From Table 2.2, the modulus of subgrade reaction K was determined to be between 4 and 6 inches, depending upon the design. And Table 2.3, the traffic was determined to be Category A for autos, pickups, and panel trucks. And the last table, 2.5, the spacing between the joints will be at a max of 15 feet. For alternative 1, we'll be using a rigid PCC pavement design. It'll be a more cost-effective approach with basic stormwater management practices such as grates and inlets to maximize parking. GI practices will be included, such as landscaping. For alternative 2, the rigid PCC pavement design, it will include more extensive GI practices such as landscaping, trees, and impervious cover. It'll also include curbs and islands. I'll be handing it off to Blake Donahoe to talk to you about the water resources component of the project. Thank you.
Hi, I'm Blake Donahoe, and I'm the lead water resources engineer for this project. The goal of this part of the project is to design a series of low-impact runoff control features to reduce the peak flow resulting from storms, as well as to improve the quality of the water that runs off from the office suite and parking lot of the new engineering building at Tarleton State University. The client requested that the Harris County LID Design Criteria Manual be referenced for this component of the project. This literature dictates technical criterion in which the runoff management and treatment systems and components must be designed to meet. Generally, the manual also states that eligible LID practices to be considered will result in a reduction and disconnection of impervious cover, as well as an increase in the initial abstractions of the rainfall impacting the site. These various LID design components may be implemented into the runoff management and treatment flow train design alternatives. Each of these components offers some increase in the time of concentration and attainment of runoff in the site. They also have varying abilities to treat the water quality running off from the site. Which of these components will be selected and how they are chosen to be implemented will be designed according to a decision matrix based upon a reduction in the peak flow of runoff, the degree of runoff water quality improvement, and the ease of their implementation and maintenance, as well as the amount of space in which they require. One design to be considered is for stormwater to impact a green roof, as well as a parking lot constructed from pervious pavement. Excess rainfall from this green roof may then be channeled to a rainwater collection cistern for it to be later reused as gray water. Remaining runoff within the runoff management and treatment system may then be diverted into a vegetated swale before flowing downstream. One of the many potential alternatives to this design may be for stormwater to run off instead from a traditional roof into a planter box or many planter boxes. Excess rainfall impacting the parking lot, whether it be pervious or not, may also be diverted into planter boxes. Underdrains may then transmit runoff into rain gardens from these planter boxes for further detention. Noah will now present the environmental component of this project.
Good afternoon, ladies and gentlemen. My name is Noah Easom, and I'm the lead project engineer for the environmental component. The current site chosen for the construction of the office suite building has average lead levels of 800 milligrams per kilogram, and the client has been advised by EPA to reduce these contamination levels to 400 milligrams per kilogram. In order for us to effectively reduce these levels down, we need to connect any pertinent historical data pertaining to the origin of lead in the soil, and also interpret the lead analysis data to identify the concentration by its depth and the types of lead species based on these samples. The good news is lead is known to be highly immobile in soil due to its strong sorption abilities with clays and silts, so we can assume that the lead is fixated to this site only and don't need to worry about any preventative measures to keep the lead from moving beyond this site. The alternatives we'll be looking at is extraction by soil washing, electrokinetics, and immobilization through solidification. Through soil washing, we'll be able to separate the coarse and fine aggregates and be able to apply chelate solution, such as EDTA, when needed to help dissolve the lead particles into solution. From there, we can physically wash the soil, remove the chelate solution or water solution, and send the soil back for repaction on site. As we can look at the table to our right, we have our untreated soil level and lead reduction percentage in treated soil. And we can see that the percent reduction depends on the type of solution we use, the size particles, as well as what the predominant lead species was. The electrokinetics will be able to remove heavy metals by applying an electric field through anodes, and then the cations that are bound to the soil will migrate towards the charged cathode. And from there, we have separate circulation systems filled with chemical solutions that will capture the lead. Then we can send those chemical solutions off site for treatment. With electrokinetics, we wouldn't have to worry about any non-metallic particles being affected. But the other thing is that the cathode and the anode distances will depend on the contamination properties within the soil. And with immobilization through solidification, it is highly suited for soils contaminated with metals and can be done by mixing contaminated soil with the correct ratio of binder, stabilizer, and water. The good news is solidification has been widely tested and implemented at Superfund sites and is considered as to be an extremely reliable alternative. If we look to the table to our right here, we have different types of locations as well as their untreated lead levels and treated lead levels after 28 days. And all of these locations had well over 50% reduction. And we can look at our estimated project timeline here. If you guys have any questions about our project timeline, please let us know in our meeting on Friday. I want to thank you guys for coming out today again. Us with Ducking Engineering really appreciate you taking the time to see our project. And if you have any questions or concerns, we'll be more than happy to hear them. Thank you.